Welcome back to Lahari tutorial. So in the last video we are discussing about a valence bond theory. Students, today we shall discuss about crystal field theory. So according to the crystal field theory, the bonding between metal and ligand arises from a purely electrostatic model. Here, according to the CFT, the d orbitals, the degenerate d orbitals are split into two sets of energies. So now let us discuss some postulates of a CFT. The transition metal ion is surrounded by the ligands with a lone pair of electrons. Here every complexes have a metal and the ligand. Here the transition metal ion is surrounded by the ligands with a lone pair of electrons. So the central metal which is surrounded by the ligands with lone pair of electrons. So the second one is all the types of ligands are regarded as a point charges. Here the ligands are considered as a point charges. The ligands may be ionic like a fluoride, chloride, cyanide, etc. So the molecules such as aqua, ammonia and carbonyl, etc. are also considered as a point charges irrespective of an ionic or a neutral molecule. The third one, the interaction between the metal ion and the ligand is purely electrostatic. It is very important. So in a crystal field theory, based on the electrostatic model, the complete theory will be explained. Here the interaction between metal ion and the ligand is purely electrostatic. So it is explained based on the electrostatic model. The next one is, in transition elements, d orbitals have unpaired electrons or paired electrons. Whenever these elements are approached by another species like a ligand, these electrons experience certain repulsion and the energy of 5d orbitals become delocalized. It depends on approach of the ligand. The d orbitals split themselves in order of their energy. So here it is simple. The transition elements, that is the transition elements, d orbitals have unpaired electrons. It may have a unpaired electrons or a paired electrons. Whenever these elements are approached by the another species like a ligand, so here the transition metal, it may having paired or unpaired electrons when it is approached by the ligand. So there is some repulsion occurs between the metal and the ligand. So due to this repulsion, the degenerate d orbitals will be split into different sets of energy. See, we know that there are 5d orbitals. Okay, these are d orbitals. So here namingly we can call it as dxy, dyz, dzx, dx square minus y square and dz square. Okay, these are 5d orbitals. So when the repulsion occurs between a metal and ligand, these 5d degenerate orbitals, it will be split into two sets. Okay, the one is Eg and another one is a T2G. So here it is the Eg set and the T2G set. So here we know that the shapes of orbitals. Yes. So here, see, there are 3 d orbitals, which are the lobes of d orbitals are lying in between the x and y axis. We know that the shape of an d orbital is double dumbbell shape. Here the lobes, here these lobes are lying in between the axis. Okay, so here the lobes are in between the y and z axis, and here x and z axis, so that this set is called T2G. And here the lobes are present along the axis. Yes, the lobes are present along the axis, so it is named as a dx square minus y square. And here the lobes are present along the z axis, so it is called as a dz square. And this set is called EG set. So here, in every geometry, particular geometry, the splitting of d orbitals will be different. So based on the repulsion, repulsion between the metal and ligand, these will be split into two sets, T2G and EG. So the last postulate is, due to the electrical field of the ligands, the energies of 5d orbitals of the metal converts into different sets of orbitals having the different energies, called crystal field splitting. So here, due to the electrical field of the ligands, the energies of 5d orbitals of the metal converts into different sets of orbitals having a different energy is called a crystal field splitting. So now let us discuss the crystal field splitting in octahedral complex. See, before that, let's consider the d orbitals. This is called degenerate d orbitals. This is called hypothetical degeneracy. So here, based on an approach of a ligand, the repulsion occurs between the ligand and the metal. So here, based on that repulsion, the degenerate d orbitals will be split into two sets, that is Eg and T2G. So in case of a octahedral, so here it is split into Eg and T2G. So where the repulsion occurs in a less amount, it will be goes to the higher energy level. Here in case of a octahedral complex, it will be split into Eg and T2G. So here the energy will be 0. So we know that the T2G set means the lobes are present in between the axis. Okay, here in case of a EG, the lobes are present along the axis. So actually it is depends on the arrangement of ligands in a geometry. So here in case of the octahedral complex, the ligands are exactly to the corners of a cube, so that here the lobes are present along the axis, so that it has a higher in energy. So in case of a tetrahedral complex, it is just reverse. So the ligands are arranged in a geometry that is in between the axis. So there is no exactly point towards the ligand, so that the higher energy, so there is a repulsion occurs in a eg set in case of a tetrahedral. Okay, this is in case of octahedral complex. So in case of a tetrahedral, so the splitting will be T2G and Eg. So the T2G will be in a higher energy and the Eg will be in a lower energy. So we have to find the crystal field splitting energy. It is denoted by delta naught. So we can calculate as here this in this portion, that is in case of a Eg, the energy will be okay. For more videos and information, please subscribe my channel. Okay, here the delta naught is a crystal field splitting energy. Here the Eg set having a higher energy than this T2G set. So how many orbitals here? There are 5 orbitals. We can write it as 5. It is a more energy comparing to this one, comparing to these 3 orbitals, that is 3 by 5. Similarly here it is less energy by the Eg set. There are 2 orbitals. Total orbital is 5, that is 2 by 5. So it is reverse in case of a tetrahedral complex. Thank you.